Hello, everyone, and thank you all for joining us. Today's webinar is Chemically Resistant Polymers for the Next Generation Healthcare and Consumer Products, and is presented by Avient Corporation. Your presenter today is Dr. Zachary Zander. Dr. Zachary Zander is a polymer scientist with 10 years of research experience. In 2018, he joined Avient as a member of their Technology Leadership Development Program and is currently supporting the specialty engineered materials business as a senior R&D engineer. His research focus has covered a broad range of topics, including electrical vehicles, flame retardant solutions for oil extended elastomers and antimicrobial technologies, and disinfectant resistant materials. To date, he has submitted 4 patent applications for Avient and is a 2-time recipient of their annually awarded Global Technical Excellence Award. My name is Carly Shader with UL, and I'll be moderating today's webinar. Please send us your questions by typing them in the question box located on your screen. Our panelists will answer them at the end of the presentation. We are recording today's event and will send you a link by email when it has been posted to ulprospector.com. Now I'd like to turn the presentation over to Zach. Would you like to begin?
All right. Thank you, Carly, for the introduction. Good morning, good afternoon, and good evening, depending on where you're joining us from. I'm really excited today to talk to you about chemically resistant polymers for next generation consumer and healthcare products. In today's webinar, we'll cover a variety of topics, starting with disinfection and cleaning, give a few examples of applications where this matters, and talk about some of the challenges that disinfectants can pose to materials. Then we'll talk more about environmental stress cracking specifically. We'll define it, give a detailed mechanism, and suggest some potential ways that you can improve the resistance of your materials. And then we can talk about the chemical resistance test methodology that we use in the lab. And then we'll share some results of our new Trillium EdgeTech product lines compared to some of the incumbent materials in the market. So today, we clean and disinfect surfaces now more than ever. Recent epidemics and pandemics such as Ebola, SARS, COVID, as well as the emergence of antibiotic-resistant bacteria such as methicillin-resistant Staph aureus have highlighted our need to prevent the spread of disease and infection. This is not necessarily new in the healthcare industry where infection prevention has been critical. Healthcare or hospital-associated infections, often called HAIs, are a known multi-billion-dollar problem that lead to extended hospital visits and extended care and costs, and even sometimes death. So enhanced disinfection and cleaning can also, however, lead to material failure, and that'll be the focus of the webinar today. So here's a few examples of where disinfection might matter. All of these are examples of high-touch durable surfaces, and one thing you can note is that many of these applications cannot be sterilized through conventional means of ETO or autoclaving. These are all surfaces that are being treated on a very regular basis with either sprays or wipe that are disinfectant to try and help prevent the spread of pathogens. And so a few examples are infusion pumps and healthcare monitors, and the consumer industrial, you've got point of purchase devices and kiosks. So I want to talk a little bit about what are these disinfectants, from both the healthcare and the consumer industrial markets. You can see a lot of commonalities between them, but also a few differences. So I just have listed here some of the more common ones that we're aware of. You can see things like Cabicide, which is pretty popular in the healthcare industry, and then Clorox and Lysol are all-purpose cleaners for the consumer industry. And so what do these have in common? Many of them will utilize an active ingredient that's called quaternary ammonium compounds. And these compounds are positively charged ammonium head groups with a long nonpolar tail. And they're pretty effective cell wall disruptors, and so they're pretty effective against bacteria and other microbes. But sometimes you'll see too that the active ingredient could be something like a hydrogen peroxide or a phenolic. And so there's a bit of a variety. But one thing that I think is important to note is that I think many people fall under the conception that, oh, it has QAC. So if my material fails because of these quaternary ammonium compounds, it's because it's sensitive to the quats. But the reality is that oftentimes, if you were to compare, let's say, Cabicide and Virex, for instance, the difference really can be in the other relevant ingredients here. So there's things like 2-butoxyethanol, diethylene glycol-butyl ether, maybe dipropylene glycol, which oftentimes can be more detrimental than the disinfectant or the active ingredient itself. So it's important to watch out for some of those things. And another thing to note too is that the pH range can be pretty broad. So if you have something that's sensitive to acid or something that's sensitive to base, These disinfectants can cover a really broad range of pHs as well. And so now we've talked a little bit about disinfectants. I want to talk about just the general material options in this field. So in general, most materials will fall under the category of being amorphous or semi-crystalline. And the thing to note is that amorphous materials are generally going to show a lower or poorer environmental stress cracking resistance than their semi-crystalline counterparts. And the reason this is, and we'll get into more details later on, is that they have a higher free volume and they have more chain mobility. And they also do not have the barrier capability that a semi-crystalline material would have. Some of the benefits of an amorphous material are that they exhibit low shrink rates. They also tend to have good impact, and they can be made transparent. So a few examples include PC, PCABS, copolyesters. And then in the semi-crystalline, as I mentioned, have better environmental stress cracking resistance, which is imparted by the crystallinity. It provides a barrier. It also reduces chain mobility. However, the drawback because of this crystallinity is that they tend to show higher shrink. So it's something that has to be planned for. They also tend to show a little bit lower impact, and they're mostly opaque. Some examples here are PCPBT, where the PBT is primarily bringing the crystallinity, polyketone, POM, and also other polyamides. And so a few other considerations when you're looking at your material options that you might need to consider are ISO USP biocompatibility. So if it's a class 1, class 2 medical device, there might be some need for an ISO 10993 skin contact approval. Or for instance, some other things to consider include flame retardancy. And the flame retardancy can be particularly challenging, especially if you're looking for a very thin-walled application and you need a non-dripping formulation. That can be sometimes difficult to achieve. And there's also additional regulations that are being made around flame retardants in terms of whether they're including halogens, no halogens, and so forth. Finally, part design and costs are always additional considerations, and we'll talk a little bit more about part design later. So what types of actual problems do these disinfectants pose to materials? Below in these images, there's a few pictures of like what can happen when a material is exposed to a disinfectant. And these are tensile bars that are in a lab setting where we put them in a strain jig and treat them with a disinfectant. And so in the image on the left, this is what you see here is crazing. And crazing happens because you have these little microvoids that are forming perpendicular to the stress. And those microvoids will start to propagate, and it'll appear as these little lines that are going across the bar. As crazing develops and these microvoids continue to grow, and eventually it'll crack, such as the image shown in the middle here. You can see very obvious cracks to the naked eye. And as those cracks propagate, it'll also lead to a brittle failure. And so in the image on the right, you can see this is one that actually failed relatively quickly. There's not a ton of crazing that you can see. So this is a relatively fast failure that led to just a brittle fracture. And so overall, you can see that, in a short time scale of lab experiment here, these materials are failing, and there's overall a need to improve this chemical resistance. So now I want to define what is environmental stress cracking. It's a premature embrittlement and crack propagation that leads to material failure caused by the synergistic action of stress and chemical exposure. And the second part is really critical. It's the combination of stress and chemical exposure that really accelerates the timeline to failure. Just a few fun facts are that environmental stress cracking is believed to be responsible for nearly a third, some literature says a quarter to a third of all plastic failures. And another thing to note is that the applied stress, if any is applied, is often below the level which normally would cause mechanical damage. And so what we're talking about is if you're looking at a stress strain curve for a material, you would say, this material I know it's going to yield at 3%, for example. The critical strain that's required for stress cracking can often be a fraction of that percentage. Another thing to note is that environmental stress cracking can be thought of as an accelerated creep. So this is interesting. This is why I made the point that it's the synergistic action of stress and chemical exposure, because just stress alone can cause a material to creep. But when you bring in a chemical exposure, such as a disinfectant or some solvents within those disinfectants, they can really accelerate this creep phenomenon. And they have a parallel mechanism for material failure. So let's talk a little bit more about the specifics of what causes environmental stress cracking and why. I'll first cover a few factors and then go into the mechanism and also some of the features that we can include, try and impart in stress cracking resistance to our materials. So we look at the frequency of cleaning. As we said previously, it's more so now than ever in our history. And oftentimes materials were not designed for that. So if you're planning for a product that's, let's say, going into a household and it's being cleaned maybe a monthly basis or semi-annual basis, I think your design for that material is going to be quite different than if you're going into a healthcare application where it's being cleaned every single day, multiple times a day. So the frequency of cleaning is an obvious factor. However, what's not so obvious is that there are some case studies where, let's say, the molder was using a mold release spray, and after a single exposure, that material failed. So how is that, or why is that? A lot of that comes down to the polymer solubility and its interaction with the cleaning agent or the chemical that it's being exposed to. And so on the figure on the right, what you're looking at here is a polymer solubility sphere. It's a three-dimensional plot that's defined by the Hansen solubility parameters. And so all materials, all organic compounds can be described by their intermolecular forces. And they can have polar-polar interactions, dispersive interactions, as well as hydrogen bonding. And the culmination of those interactions for a polymeric material will define what's called the polymer sphere, solubility sphere. And this sphere has a radius associated with it. And so what you can do is you can take a solvent or a reagent and you can compare its intermolecular forces with that of the polymer solubility sphere. And it can give you some indication as to whether or not that reagent is going to be a good solvent, a theta solvent, or a bad solvent. And so there's an equation that's fairly simple to use, and a lot of these Hansen solubility parameters are available online. But what this equation does is it tells you the distance of the solvent and its relation to the center of the solubility sphere. And so when the distance between the solvent and the polymer when that distance is smaller than the radius or inside of the radius, you might be able to conclude that that would be a good solvent, or at least a theta solvent for that polymer. So we did a little exercise with polycarbonate and took a few common ingredients you might find in disinfectants, such as 2-propanol and diethylene glycol ether. And what we can see is that 2-propanol falls just outside of the radius, the solubility sphere for polycarbonate, the distance being 9.3, whereas the radius is 6. And then for diethylene glycol ether, the distance here was calculated to be 5.6, so it actually falls to the solubility sphere. And so what you might be able to conclude from this is that if there was a damaging component or a component that would, in a way solvate or at least swell the polymer here, it could be the diethylene glycol ether. So this is something to consider, and we'll talk a little bit more too in the upcoming slides about how solvents influence the overall mechanism. The final factor is in residual and applied stresses. So residual stress in the part can develop from two different things: processing parameters as well as part design, and these oftentimes go hand in hand. From a processing standpoint, it would be really great if we could inject everything super fast into a really cold mold and inject a part in 2 seconds. However, when you go about doing it that way, you're going to develop a lot of internal stress in the part. And there's also ways through part design that you can help to eliminate some of those internal stresses, but processing and part design go hand in hand. The images down here on the left, this is just a mold flow simulation that shows what the residual stress in the part would be, so it's an approximation. The image next to this is an image of the mold shrink, so the red being higher shrink and the blue being lower shrink. And so a lot of times where you see the higher levels of shrink, there's commonly some residual stresses associated with those as well, mostly because the chains are being frozen and the stresses are being frozen into the part. So what can you do from a part design in order to try and help reduce residual stress? This slide was prepared by our Avient design team. I will admittedly say I'm not an expert in design, but we have those in-house, so that's good. When it comes to part design, there's a few things you can add, and one of the more important ones that I heard of is a coring feature. So what a coring feature does is when you're designing a corner in a part, the coring feature will help you maintain a constant wall thickness around that corner. It also makes the transition of the corner much smoother. So this will help alleviate some of the stress that you might see in a sharp corner of a part. A few other things such as gussets and ribs, as well as bosses to reinforce edges. These things can help to reduce warpage in a part. They have to be strategically placed. It's not simply by adding them will it ultimately, eliminate your issues of warpage, but in a strategically placed manner using the appropriate conditions, these can prevent warp and eliminate fluid pooling. So that's important because if a part warps and creates a depression and it's being routinely sanitized and the fluid's allowed to pool, that can definitely lead to environmental stress cracking. The final thing from a part design perspective is to have minimal holes. So a lot of the applications we're talking about with device housings are going to have holes for buttons or for displays to come through. And so one of the things that helps is to have round or oval shaped holes. and to have them parallel to the flow path of the material during processing. So let's talk a little bit more about the detailed mechanism of stress cracking. So in the image over here on the left, what you can see is like a tensile bar or a flex bar that's in a bent configuration. So we're applying an external stress to this. And on the top side here, you're going to have tensile stresses that are developing. And on the bottom, you'll have compressive forces. And so what happens when you take a material and you apply a stress to it is that these chains that normally exist in somewhat of a random configuration or a random coil, maybe in a tensile bar a little bit more elongated than this, but what happens when you have that external applied stress is that those chains are going to start to align. They're going to have some mobility. They're going to be able to slide past one another and rotate, and if it's within the critical strain of the material. And as those chains move around and reorient, what they'll do is that free volume, they'll leave behind a voided area, so microvoids. And as these microvoids start to develop, you can start to see crazing on the part in a plane that's normal or perpendicular to the stresses. And so that's what we see as crazing. And as those cracks or as those microvoids continue to grow, eventually the stresses can become too much for the chains, and you'll see chain pullout or potentially chain scission, which will ultimately lead to cracking and then moving the stress down into the deeper layers of the part. And so you can see how this thing would sort of propagate and lead to brittle fracture. And so you might be thinking, well, what about the solvent? What about the environmental portion of the stress cracking? What a solvent really does, and it doesn't necessarily have to be a good solvent, but what it really does is it reduces the critical strain needed for these chains to align. And so when that solvent gets in there, it increases the free volume, it increases the mobility of the chains, suppresses the glass transition of the material. And sometimes, for example, in an amorphous material, the solubility of the diffusion of the solvent into that amorphous material can actually create osmotic pressures that impart even more stress to the part. And then the last thing to bring up here too is that there's an observed phenomenon called stress-enhanced fluid absorption. So where your part is under the highest amount of stress, it'll tend to uptake the most solvent. And this is a function of just reducing its free energy. So it wants to localize that solvent to the area of stress so that the material itself can relax in response to that stress. So that's a little bit of a mechanism of how environmental stress cracking proceeds. And so you might be thinking, well, what can we do to try and influence the resistance of our material? And so I think the first thing to bring up when it comes to environmental stress cracking resistance is that crystallinity can go a long ways to improving a material's resistance. And the reason that crystallinity helps in environmental stress cracking is because it presents a barrier to the uptake of the solvent or the chemical reagent that it's being treated with. And so if you're looking at these system of equations here, what this is essentially showing you is the diffusion resistance for a material. And in an amorphous material, the R0 is just normalized to 1. Whereas in a semi-crystalline material, you take into account the surface area of the crystallites divided by the number of amorphous channels and the volume fraction of amorphous channels. So in the total equation for diffusion resistance in a semi-crystalline material, you're adding the surface area of the crystallites as well as the volume fraction of the crystallinity. So what that means is the larger the crystals and the more crystals that you have in your sample, the better the diffusion resistance is. And that's important because ultimately, when the disinfectant or the chemical reagent it's being treated with penetrates into the sample, it improves the mobility of the chains. And chain mobility is what allows these things to stress crack. And so for an amorphous material, what can you do? Like, let's say I have a transparent part, it needs to be transparent, I cannot add crystallinity. Well, molecular weight is probably the easiest lever to pull for an amorphous material. And when you go to higher molecular weight, you're going to have more chain entanglement. As long as you're above that critical molecular weight of entanglement, the viscosity, however, is also going to increase. And so this might create some challenges when you're going to process the material. If the viscosity is extremely high, it could also impart more residual stress during the molding process. So there's a little bit of a balance here where you want to have more chain entanglement, you want to have less mobility, but also it becomes more difficult to process. So then what else can you do in terms of influencing the stress cracking resistance here? Well, number one is changing the solubility parameter of the system. And so the ways that you can achieve that is through polymer blending or also through different backbone chemistries. Different backbone chemistries are going to have different solubility parameters, right? So if you're looking at, let's say, a polycarbonate, you might now switch to a copolycarbonate that's going to have a different chemistry that might show a little bit better diffusion resistance or overall lower solubility to the disinfectant that it's being treated with. Another way that this can be achieved is through polymer blends. So if you're blending in, for example, PBT into a polycarbonate, that PBT is going to, well, number one, it's going to bring some crystallinity, but it'll also change the solubility parameter of the system. So maybe a better example there is PET, rather. So I want to talk a little bit about how do we test for chemical resistance in the lab. And I'll start with the one on the right. ASTM 1693 is a test for ethylene plastics. This was originally created because they noticed that cross-linked polyethylene tubing and wire and cable were showing failures in the field because they were frequently being treated with surfactants or soaps to help feed the tubes and the wires. And so this is really kind of specific to ethylene plastics. And the reason that is because they have a very high strain in this test. The bars are being bent almost 180 degrees. They're submerged in a chemical solution and they're tested for, upwards of, 60 days or so until the material fails. And then they use that time point as the metric for how resistant it is. This test isn't really designed for all materials, especially a lot of those going into the healthcare industry, which are oftentimes engineering resins. So the ASTM D543 method is also commonly used for looking at chemical resistance and environmental stress cracking resistance in particular. This method takes tensile bars and potentially flex bars as well, puts them into a strain jig that has a fixed strain of 1 to 2%, which is meant to simulate molded stresses. And then what you do is you'll apply a disinfectant and a gauze soap pad to the middle of these bars for 72 hours, typically 72 hours, but there's a lot of different adaptations, some of which are listed here below. For example, you could, instead of applying a gauze soap pad, you could do a repeat wipe testing, which I've seen done in the industry. You could also have wet to dry cycles where, as that disinfectant dries out, you reapply a freshly soaked gauze pad. This is the method that we tend to use. And then also there's other deviations where, maybe you'll test it on the impact bar instead of a tensile bar. So a lot of how you do this test depends on what you define as your critical requirements. So we do the ASTM D543, and I want to show you some of the results that we've had with our new materials, the Trilliant and EdgeTech 8900 series. In the image on the left, what you're looking at is a bar graph of a tensile retention data. So when you do this test, typically you'll have a strain control that's put in the strain jig at the same strain level, and it's not treated with a disinfectant. And then for your test group, you'll be treating that with the disinfectant, and you'll compare the tensile properties. And you do that by dividing the test group versus the control group. And that'll give you a percent retention value. And so what you aim for in this test is 100% retention. Going above that or below that could be equally bad things. So the values we look at here are strength at yield, elongation at yield, as well as elongation at break. So these are telling you your failure points of the material. If it yields, that's already kind of failed in the field, right? The elongation at break gives you a little bit more insight into, whether you've seen some chain scission or whether you've had some weakening in the spot of the treatment area. And so on the image on the right, what you can see when we did this test with Virex TB, our Trilliant HC8900 series, as well as the FR copolyester, did not really exhibit signs of stress cracking. The PCABS, FR PCABS, and PCPET actually failed in the strain jig, so you might be able to see the cracking in the bars there. So that's why there's no data here for those. As I said, the FR copolyester didn't exhibit signs of crazing or stress cracking. However, you can see that there's a notable loss in the mechanical properties, whereas the Trilliant material showed almost nearly 100% retention. We did a similar thing for our consumer product line, the EdgeTech 8900 series, where we looked at Lysol all-purpose. We've also tested a number of other disinfectants, which I'll show on the upcoming slides. But again, here, what you can see is that there's really no visual signs of stress cracking. PCPBT actually also held up pretty well against Lysol in this test in terms of the visual observation. But the FR PCABS, you can see maybe some cracking here, but definite signs of crazing. And the same on the PCPET. Again, you can see obvious signs of crazing in that part. And so when you look at the tensile data, that can also help you interpret, what sort of damage has been done to the material. Again, targeting 100% retention, which you see for the EdgeTech series, the base grade, the high impact, and the FR. And then for the FR PCABS, a very significant loss in properties here, PCPET as well. And the PCPBT showed a significant loss in elongation at break, as well as some of the yield strength of the material. So then how do we ultimately define the performance of these materials? We've developed an internal criteria or a rating scale for these materials. And all of this is basically what I just talked you through, putting that into a scale. So number one, did the samples survive the disinfectant exposure in the strain jig, or did they fail entirely? So you get a plus for surviving the strain jig. And then there's the visual observation score. This is a 5-point scale that our technicians provide, where a 4 or a 5 represent minor or no crazing, as well as definitely no cracking. So that's another criteria. And then the final 3 are dependent on the tensile retention data. So if there's no statistically significant reduction in the elongation of break on a 95% confidence interval, we'll give it an additional plus. And then the retention of the strength and the elongation and yield are also the other criteria. So can it retain between 75 and 100 or 100 and 125% of its original properties relative to the strain control? And then even a little bit more difficult, retaining 90 to 100 and 100 to 110% of the strength and elongation and yield. And so then we summarize this in a table. And as I said, we tested against a number of different disinfectants that are listed here. And so all of these are pretty common healthcare disinfectants for our Trillium materials that we tested against. And again, you can see, FR-PCABS, PCPT, failing in the jig against Virex TB, which is one of the more difficult ones, also poses some problems to the FR copolyester as well. And so overall, the Trillium materials here perform very, very well against this swath of disinfectants. And so how does this compare, or how does the Trillium material compare to some of the incumbent materials in the space? This is an example of the properties for our flame retardant grade, 8920, compared to some other FR PC alloys as well as FR copolyester. So one of the things you might notice off the bat is that the mold shrinkage is a little bit higher. And so these materials are made out of an aliphatic polyketone blend. And so that polyketone imparts some crystallinity. And so being semi-crystalline, again, it'll tend to have a higher mold shrink, much more comparable to something like a PCPBT. In terms of the tensile and flexural properties, you'll see across the board that these materials are in the same ballpark. The heat performance, HCT 0.45 and 1.8 megapascals, is also quite comparable, falling somewhere in between a PCPBT and a PCABS. And the last thing that's also important here to note is the UL94 rating. So when we tested these internally, we're able to achieve a 5 VA at 3 millimeters, V0 down to 1.5, and a V1 at 0.75. So these formulations do not have a tendency to drip, which can be a very difficult problem to solve. One other thing I'd like to note is that the flame retardant system for our Trillium and EdgeTech materials is completely halogen-free. So here's another example. Now this is looking at our EdgeTech materials. We have our base grade, the high impact grade, as well as our FR grade. And in this space, we tested against a variety of different disinfectants or cleaners, such as Clorox, Formula 409, and Lysol. One thing to note is that Formula 409 is not technically a disinfectant, since there are no active ingredients. But at the time that we were doing this testing, it was sometimes difficult to find the disinfectants. But there are other relevant ingredients that do pose problems, which you can see here with the PCABS, PET, and PBT, that the Formula 409 definitely poses some challenges, as well as the Lysol purpose cleaner. So once again, though, our EdgeTech materials, the T8900 series, perform very well in our visual observation and our tensile retention data. And then a quick overview again of the physical and mechanical properties, essentially the same thing as for the healthcare slide. So in the consumer space, now we have our high impact grade that has a little bit higher mold shrink relative to some of these other ones. But when you're looking at the tensile and flexural properties, again, pretty comparable across the board. Again, these are all FR incumbent materials, so it's a little bit more direct comparison to these, or the ET 8900, 8920 grade, I should say. But one thing I did want to highlight is that for a semi-crystalline material, the notched ISO performance, it can be lacking at times. This is in part because the notch sensitivity that exists for a semi-crystalline material. So we did want to show our high impact grade here. We can achieve a relatively high notched ISO performance if that's a critical part of the requirements for the application. And then lastly, again, the UL94 rating, same as before, 5VA, V0, and V1 down to 0.8 millimeters. So we've talked a bit about disinfecting, the increase that we've seen in disinfection. We talked about the mechanism of stress cracking, and maybe some things that you can do to try and improve the resistance of the materials towards stress cracking. And we also presented some test methodologies and the new materials, the Trillium HC8900 and EdgeTech ET8900 for healthcare and consumer industries, respectively. Some of the key features that I'd like to just highlight about these grades is that they are exhibiting best-in-class chemical resistance with comparable physical and mechanical properties to some of the incumbent materials in the space. They're formulated without EPA ingredients, and they're also utilizing a non-halogenated flame retardant system. And so with that, I hope that you found this helpful, and really looking forward to any questions that you might have. Thank you for your time and your attendance.
Thank you, Zach. And we'll kick off the question and answer portion here. Just as a reminder, if you have a question, please type it in the question box located on your screen. In addition, one of the questions that has come in is, can the recording be made available afterwards, please? And the answer to that is yes, we are recording today's event, and you will be receiving a copy. And with that, we'll get started on our first question for Zach. What is the product made of?
Yeah, so as I kind of alluded to a little bit before, it's a aliphatic polyketone blend. And polyketone is a material that was developed for oil and gas barrier properties. So this material itself has really good performance in terms of its chemical resistance. But we've also found through synergistic blends that we were able to even accentuate that performance as well as to improve the stiffness of the material.
Thank you. And our next question is, what type of regulatory are these materials engineered to pass?
Well, in terms of regulatory, for our Trilliant product line, which is our healthcare material product line, all of the resins in that formulation are ISO 10993 or USP Class 6. So we do not have ISO or USP certification on these yet, but we're willing to work with our customers on that. The other thing is the UL yellow card. So this is currently pending. We're in the process of making samples for that right now, but the test results we have are from a UL accredited laboratory.
Thank you. And the next question is, what is the difference between the healthcare version and the consumer version?
Yeah, so the healthcare version is formulated with ISO 10993 and USP Class 6 resin. And so that's the key difference here.
Thank you. The next question is, what kind of sterilization data have we tested for these products?
So in terms of sterilization, we do not have data currently on this. So the purpose of this material was really to fit the market need where things are being routinely disinfected. So products that cannot be sterilized because let's say there might be some sensitive electronics involved. So we do not have sterilization data. The purpose here was really to target those that are suffering material failures from the routine disinfection.
Thank you. The next question is, can this be a drop-in replacement for PC/ABS?
So in terms of mold shrinkage and whether or not this is a drop-in replacement, it's really going to depend on part geometry, the wall thickness of the part, as well as the processing parameters. There is clearly a difference in the mold shrink, especially relative to like PC/ABS. So it might be a difficult thing to do, but I would certainly encourage trying it, working with our ADTS team. They may be able to get you there.
Thank you. Our next question is, what is the reason that semi-crystalline polymer has better chemical resistance, and does crystallinity level of polymer increase chemical resistance?
Yeah, absolutely. I think that the crystallinity level of the polymer will increase the resistance. Again, if we look back at the diffusion resistance equation, you'll see that the surface area as well as the volume fraction of crystallinity are the two main contributing factors to preventing diffusion into the sample. Another thing to note is that the polymer backbone chemistry can also influence your resistance. I think maybe over a longer period of time. It's been said that with regards to environmental stress cracking, the chemical reactions are happening on a slower time scale than what this phenomenon might. But you might see other issues like discoloration or something over a longer period of time if you have some chain scission of the material from those disinfectants. And so the backbone chemistry of the polyketone, for example, is all saturated. So there are no ester bonds or carbonate bonds that can be, prone to hydrolysis, for instance.
Thank you. Our next question is, which impact test should be performed after being tested? CHARPY, CHARPY, or IZOD test, IZOD?
Well, so that's it's going to be dependent on the application. One of the things, there's other ways to test impact as well. There's instrumented impact. I will say that when you test a material in a notched setting, semi-crystalline materials or blends are always going to perform worse. They have notch sensitivity. So whether it's a notched Sharpie or a notched Izod, there's going to be a notable difference in a semi-crystalline material. But oftentimes, if you were to look at like a drop dart or an instrumented impact, for example, or even unnotched Izod, then you can see that the practical impact is not quite as bad as what you would see with like a notched Izod testing. So I think that question, it really depends on the final application. So if the material is going to be dropped from a high distance, and if the material is, let's say, machined so that there is some post-processing notch that's present, then obviously I think a notched Izod test would be the way to go. But if you're just looking for a drop impact, then you might consider an instrumented impact instead.
Thank you. The next question is, how does the performance compare against Elcrest CRX from Sabic?
Yeah, that's a good question. We haven't done that comparison, but we are happy, and willing to compete. So I'd encourage you to reach out and ask for a sample, and we'll find out.
The next question is, are there any PCR grades available?
Not currently. We don't have PCR grades for this material, but we are happy to talk about any other sustainability benefits that you might have. Polyketone itself does offer some sustainability benefits over things like polyamides and polycarbonates in terms of their CO2 emission that's needed to produce the material. So we would be happy to talk about that a little more offline.
Thank you. The next question is, can you restate the base polymer type for the Trilliant again, please?
Yeah, both the Trilliant and the EdgeTech series here are utilizing aliphatic polyketone. It's a linear alternating copolymer of carbon monoxide and ethylene.
Thank you. Our next question is, what are EdgeTech grades for E&E applications?
So the EdgeTech grades are basically our kind of catch-all for consumer industrial. We have 3 different grades currently available. There's sort of a base level grade that is just our polymer blend. Then there's an FR grade, which will meet 5VA at 3 millimeter, V0 at 1.5, and V1 at 0.75. And then there's also a high impact grade as well.
Thank you. The next question is the Trilliant UV stabilized?
Not currently. We potentially could do UV stabilization, add that into the package as well. So be happy to talk about that offline as well.
Thank you. And the next question is the plastic mentioned UV resistant?
So we do not currently have UV stability data for these blends. It is something that we could look into.
Thank you. The next question, are you going to get FR rating for ET8900HI?
So this being a high impact grade, there is no flame retardant in that grade. If we wanted a HB, like a UL yellow card HB, that's something that we could pursue. But if we're looking for high impact and FR grade, that's something that we are waiting for a little bit more customer feedback. We wanted to test the market first with these grades to see what the desire would be for a high impact and FR grade.
Thank you. The next question is, how's the physical and chemical capability with PET?
We haven't looked at the compatibility of this blend with PET, so I'm not entirely sure.
Thank you. The next question is the polyamide material resistant to virus/fungi and bacteria or microbes, ATC?
Yeah, okay. The material itself is not antimicrobial. We do have our color and additives group does have a product line with Stand where they have offer master batches of a variety of different antimicrobials for different regulatory needs, locations, and performance levels. So we'd be happy to look into that and pull in our withstand product managers for looking at the antimicrobial performance. But the material itself is not antimicrobial.
Thank you. The next question is, do you have non-halogenated grade of plastics in your range?
Yeah, absolutely. So the ET8920, the EdgeTech ET8920, as well as the Trilliant HC8920, so that's basically consumer and healthcare. Those are all non-halogenated flame retardants. We do not utilize, PTFE or any kind of anti-drip in those formulas either. So these are zero halogen flame retardant systems.
Thank you. The next question is, we have migrated away from PC/ABS and healthcare applications for our products in lieu of a very expensive chemical resistant material, which also meets our high standard for impact resistance. Is there any progress in improving impact resistance for the HC offering?
Yeah, again, so I think that's certainly in the scope of what we hope to do. It is something that we've looked at. So we're planning to test the market with the materials that we currently have available to see what the interest for that would be.
Thank you. The next question is, what minimum thickness can I manufacture?
So this I'm not really sure of, to be honest. We've molded flame bars down to 0.75 millimeter, for instance. I'm not entirely sure what the minimum thickness would be. We do have a very strong ADTS team that can help provide technical support and also potentially do some mold flow studies for you.
Thank you. The next question is Trilliant HC amorphous or semi-crystalline?
Yeah, the Trillium HC product line as well as the EdgeTech, these are all semi-crystalline blends. So they do have a degree of crystallinity to them. They are transparent as well. I'm sorry. Let me. They are opaque. They cannot be made transparent. I meant.
Perfect. The next question is the grade of plastic material mentioned has resistant against abrasion or is it scratch resistant? Does it have any self-healing property?
It does not have self-healing properties, but I do anticipate, because of the base resin, that it would have good scratch resistance relative to something like a PC.
Thank you. The next question is, what maximum temperature and dielectric strength does it offer, especially a polyamide type of plastic?
In terms of the heat performance, we've looked at heat deformation temperatures. So depending on the load, you'll see different performance. But we see at 80 degrees centigrade being the higher load, the 1.8 megapascal heat deflection temperature of 80 degrees centigrade. If you're at a lower load, like a 0.45 megapascal, the heat deformation performance could be as high as 110 degrees, depending on the grade.
Thank you. The next question is, how many products are in the Trilliant product family?
That's a good question. I'm not sure I know the answers to that one. In terms of materials for this target application, where we're looking at things that are being routinely disinfected, we do have, currently there are 3 that I am aware of. We have a copolyester grade, and we have these new HC 8900 grades as well.
Thank you. The next question is, ballpark, how does the Trilliant and PC compared how does cost for Trilliant and PC compared based on percentage?
I'm sorry, I'm trying to think of the answer to that. I'm not sure off the top of my head how they compare, but I know that our product managers and our sales team would be able to get you that answer.
Perfect. The next question is, do you have antibacterial, antivirus grades so that no need to apply disinfectant solvent for general application?
Currently, we do not have antimicrobial grades for this product line, but as I did mention before, our color and additives group here at Avient does have a withstand product line that offers a variety of different antimicrobial master batches that could be used.
Thank you. The next question is this grade suitable for VHP sterilization?
I'm not sure. We haven't tested different sterilization methods. Again, I think the target application here was for those materials or those applications where they cannot be sterilized, right? So things with electronic components, device housings, things that are being routinely disinfected that we think are going to be, showing or exhibiting failures due to this routine disinfection. So currently, I do not have sterilization data. But it is something that we could pursue together. So I'd be happy to, if you wanted to reach out, I'd be happy to talk to you about that.
The next question is, are there any transparent / translucent options?
No, yeah, sorry, I misspoke a little bit earlier. These semi-crystalline blends are opaque, so we do not have a transparent option for these products, or translucent.
Thank you. And the next question is, would these be considered green / sustainable materials?
I'd have to double check on, what our stance is for that. I know that's not the primary value proposition here, but again, there are some sustainability benefits in terms of the base resin relative to, polycarbonates and polyamides in terms of the CO2 emissions that are required to produce the material. So, I could take that one offline. I'm not sure exactly what our stance is currently on promoting that.
Thank you. The next question is, how does the chemical resistance of the copolyester grade compare to the PK grades?
So the copolyester, in general, it exhibits pretty good resistance. I will say it's not quite as good as the Trillium or the new EdgeTech 8900 series. You can kind of see that typically in the mechanical properties. So the copolyester, we've noticed, does a pretty good job of hiding any crazing or cracking. But when you look at the mechanical properties, especially towards some of the more aggressive disinfectants like Virex or like a Lysol all-purpose, you will see a notable loss in your tensile retention, which could correspond to other properties as well, like flexural and potentially IZOD performance. So the copolyester definitely will have better performance than like a PC ABS and more comparable mold shrink. But if you're looking for something that's going to have broad chemical resistance against a lot of aggressive disinfectants, that's when I would suggest the ET 8900 or the Healthcare HC 8900 series.
Thank you. The next question is, did you also test another very used material in healthcare, the PVC?
No, we have not benchmarked against PVC. I think from what I understand, PVC does have fairly good chemical resistance, but I do know that there are also some other concerns around using PVC in the healthcare setting, for instance. So we did not specifically benchmark against PVC here.
Thank you. And this will be our last question. How does the process temperatures compare to PC?
So the processing temperatures, that's a good question. The processing temperatures for this material is a bit lower than PC. So generally speaking, when we injection mold these, we try to target a temperature of about 230 to 240 degrees centigrade, whereas you might, for let's say a PC alloy, you might be closer to say 280 to 300 degrees centigrade. So it is a bit lower in terms of its processing temperature. And you don't see as much of an effect by increasing the temperature on the flow performance. So, whereas for an amorphous material, if you go to higher temperatures, generally you reduce the flow more. So there is a reduced processing temperature here as well.
Thank you. And actually, I have one more question. You mentioned that people can reach out for samples. How can they do that?
Yeah, if they wanted to contact, you can either go to our website, avient.com, or you could, I think maybe Avery or Rita's on the line. I believe that there's a request email address as well. But if you're unable to find that, you can reach out to me as well, and I can try to direct you to the appropriate person.
Yeah, we will be sending out a follow-up email that will have a link that you can click on to connect with us for any additional questions or for samples.
And Zach, this is Rita Klein as well. And just the only thing I would add to that is you're absolutely right. On our website, avient.com, we have an active chat feature, and people can always connect with our customer service team there to explore some of those answers and have immediate contact as well.
Thank you.
Great. Thanks, everyone. And thanks, everyone, for attending today's webinar. Just as a reminder, we will send you a link to the recording of today's webinar so you can watch it anytime and share it with others at your company. We will also follow up to any questions that we weren't able to get to today. And thank you again for attending, and have a great day.